In this video, we will develop some preliminary results which are required for the solution of the estimation problem. We will first derive some properties of conditional distributions of Gaussian or normal random variables. Then we will give a geometric interpretation of the results. First, let's consider an n-dimensional normal vector or Gaussian vector with a mean m. M is a vector, dimension of n by 1, and the covariance matrix R. R is a matrix of n by n. Then if this random vector is normal, then we know its probability density function can be described in this way, so that the efficacy is probably the probability density function. So efficacy will be 1 over 2 pi, so n over 2. So n is the dimension of the vector, the random vector. Determinant of R, so R is a covariance matrix, then square root. So exponential negative 1 over 2 C minus M transpose, the inverse of the covariance matrix R, and C minus M. We know a random vector or random variable can be completely characterized by the mean function and the covariance function. It is of interest to consider the properties of two vectors which are jointly Gaussian or jointly normal. Then let's introduce three theorems to discuss the properties of joint normal random vectors. The first theorem is theorem 3.3. It is stated like this. So let x and y be n by 1 and p by 1 vectors. Let's assume the vector, let's form a vector. So by stacking x and y, the vector x and y is normal with a mean mx and my. So they are vectors. So this vector dimension is n plus p by 1. So this is the same for the mean, is n plus p by 1 vector. And the covariance matrix R, so R will be n plus p by n plus p. The Rx is a covariance matrix of x, and Rxy is the cross covariance between x and y, and Ryx is cross covariance between y and x. So Ry is a covariance matrix of the vector y. Then the vector z is x minus x mean, so minus Rxy, Ry inverse, y minus my, and independent of y. And this vector z has 0 mean and a covariance matrix. So Rz will be Rx minus Rxy, Ry inverse times Ryx. The proof of the theorem can be found on page 219 in the textbook. The next theorem, theorem 3.4, is stated like this. Let x and y be two vectors which are jointly normal or jointly Gaussian. The conditional distribution of x given y is normal. Okay? If two vectors, they are jointly normal, then the conditional distribution is also normal. It's also Gaussian. So the mean, the expectation of x, the mean of x conditional y is mx plus Rxy, Ry inverse y minus my. So this is condition on y, so the y is given. This is a realization. Then the covariance of x condition on y is Ry minus Rxy, Ry inverse Ryx. The random variables y and x minus expectation, x conditioned on y, are independent. The proof of this theorem can be found on page 219 in the textbook. This statement, the random variables y and x minus the expectation of x condition of y are independent, follows from the theorem 3.3. From here, we can see the x. So this part, so my, rxy, ry inverse y minus my. So this is the expectation of x condition of y. So you notice z will be x minus x expectation of x condition of y. So therefore the z and y are independent. So in this case, it will be the y and the x minus the expectation x condition of y are independent. The last theorem, theorem 3.5, is stated like this. So let x, u, and v be random vectors with a jointly normal distribution or jointly Gaussian distribution, and let x and v be independent. Then the conditional mean of x conditioned on u and v is equal to the sum of the conditional expectation of x conditioned on u plus the expectation of x condition v and minus the expectation of x. Now let's discuss how to apply these theorems to solve estimation problem. To do so, let's take two random vectors, so x and y, they are random vectors, which are jointly normal or jointly Gaussian. Then let's consider the problem of estimating x from observations y such that the estimation error is as small as possible in the sense of a mean square. So in this case, we know the x, y, so they are jointly Gaussian. Let's assume so y is observation. We want to estimate x based on the observation of y. Then based on the theorem of 3.4, we know the conditional distribution is also normal. So the conditional distribution of x condition of y is normal. So this is the theory 3.4. If x and y are two vectors which are jointly normal, then the conditional distribution of x given y is normal. So this is theorem 3.4. We know the conditional mean is normal. Then the normal density satisfies the condition of theorem 3.1. So theorem 3.1 so states like this. So if the conditional distribution is symmetric around the conditional mean and non-increasing for c greater or equal to m. So for normal distribution, we know normal distribution to be something like this. The center is the mean. The normal distribution satisfies the condition of 3.1 regarding the density function. And also in the problem, we want to minimize the estimation error in the mean square. So in other words, the loss function, so the loss function will be just s minus x hat squared. For this function, so this function will be just the x using g, will be just gx is x squared. This function also satisfies the condition of theorem 3.1. So the loss function is symmetric around 0. The x, gx, the function will be like this. It's symmetric around 0 and non-decreasing for positive argument. So therefore, the probability density function and the loss function, they both satisfy the condition of 3.1. Then in this case, we know the best estimate is given by the conditional mean. It's given by the conditional mean. So normal density function satisfy the conditions of theorem 3.1. Then we know, so this is based on the result of theorem 3.1. So let's use x hat to denote the best estimate. We know the best estimate is the conditional mean according to theorem 3.1. Then according to theorem 3.4, the conditional mean of the normal to two normal random vector we are jointly Gaussian will be, so this is the result, okay, will be mx plus rxy ry inverse y minus xy. It will be mx rxy ry inverse y minus my. So the best estimate is a conditional mean is mx plus rxy ry inverse y minus x my. Then let's use the tilt of the x tilt to denote the covariance, that to denote the estimation error. So the difference between the random variable x and its estimate. This is an estimation error. Then the covariance of the estimation error, x tilt, conditioned on y, again, so based on the theorem 3.4, so it is Rx minus Rxy, Ry inverse Ryx. It will be Rx minus Rxy, Ry inverse Ryx. According to theorem 3.3 and theorem 3.4, we know that estimation error, the x tilde, is independent of y. It can be seen from theorem 3.4. We know that the random 3.3, we know that the vector z is x minus mx minus rxy ry inverse y minus my. Then the mx rxy ry inverse y minus my, according to theorem 3.4, is the conditional mean of x conditional y. So therefore, x minus x expectation of x condition y is independent of y. The estimation error is independent of y. So based on the theorem 3.3 and theorem 3.4. Now let's discuss how to apply theorem 3.5 to solve this estimation problem. So this problem is to estimate x based on observations of u and v, where u and v are independent. So let's use the height xu denote the best estimate of x based on the observation u, and the height xv, the best estimate of x based on v, and height uv, the best estimate of x based on u and v. Then theorem 3.4 and 3.5 implies that, to this the theorem 3.4, theorem 3.5. So indicate that the best estimate of x conditioned on U and V, so based on the observation U and V will be the conditional mean of X conditional on U will be this is the best estimate. The best estimate of X condition on U based on the observation of U plus the conditional mean of X condition V. Okay, so this is the best estimate of the X based on V, then minus the expectation of X. Then that is X.